right? So for today, I'd like to continue with where we left off and still do the overview. There are more slides than I can probably cover for today. So the handout is fairly thick. I'm not sure if we'll have time to go through all of them, right? So far, do you have any questions about what we talked about? Right. So let's continue with the overview, right? So for today, we're going to continue with the chapter 1, some of the overview of important concepts and stuff. And I'll introduce the notion of caches and asynchronous I/O, which will come throughout the operating system, right? Operating system. One thing you should remember is there's a bunch of resources, you have to manage them, and the management depends on what you're trying to do, right? So if you want to give good interactive performance, you do a certain way. If you want to do something else, you do different ways. And there are very few tools which we have in our toolbox, right? And some of the tools are, one of the biggest tools we have is cache. And I'll tell you what cache is, and you'll see that throughout the system, if things are slow, caching usually helps, right? And then we'll talk a little bit about systems calls and how applications and the OS interact and what are the different models of how people build operating systems and stuff like that. And hopefully a little bit about the booting process. What does that mean? So this is we didn't show this graph in the last class, but essentially you have the computer hardware somewhere down there, and you have the user sitting up at the top, and you can think of operating system as sort of this, the upper two blue boxes. There's the OS kernel, or the core operating system. And then there are other programs, other programs which are called systems programs, like compilers and all those things. Together, they make what you usually buy as operating system, right? When you buy operating system like Windows XP, you get the core Windows plus a whole bunch of other niceties that makes life easier. You don't just get the resource management. You get a GUI, you get an Internet Explorer, and other tools. And those are considered to be part of, to make your life nice. So they are part of the picture again, right? And to recap, one of the things we mentioned, we kind of talked about in the last class was operating systems lets you somehow, it has to load a program, load your Microsoft Office or whatever, and load it, and then run this application, right? And we'll see what running means in subsequent classes. But for now, the OS has to make sure that when application is running, whenever it wants a resource, it's given. If you want a keyboard, you give the keyboard. If you want memory or hard disk, whatever, it gives this stuff to you. And if there's a failure, it's up to the OS to clean things up, right? If a program has a failure because of a software error, because of a hardware error, whatever error, the OS duty is to make sure that the machine keeps going, right? And if the OS fails, something like what happens, right? The OS could not, so it was trying to do something, I don't know what it was, and it couldn't complete it, so it couldn't do something, so it died, right? And I can't interact with it anymore. I had to reboot it because at this point it's not talking to me, right? So the OS cannot do error recovery. You're in deep trouble, right? Some of the errors that you would have faced is software errors. How many of you programmed in C or whatever where you get segmentation fault, memory violation, stuff like that, right? So those are essentially software errors. So essentially your program tells OS something happened, and you get a software error, right? And some of them you can recover from, some of them you can't recover from, right? If you divide by 0, you get an exception, but usually you can deal with that. If you get a memory fault, usually something is basically wrong with your program that it kills your application or whatever, right? And some of the other stuff, you see the blue screen of death when the OS says, there's some error which is happening, I don't know how to deal with it. Here's a trace. If you know what you're doing, you can look at it. Otherwise, reboot the machine, right? So it's the one which gives you the resources, it's the one which controls how much you have, and it's the one which has to maintain, keep the system going. And when it fails, systems crash, right? So some of the important topics I'll mention. We'll go through them in detail later on. But essentially, one of the things to remember is the faster the thing is, the more expensive things are, right? And it's true for most of these things. The faster the processor, the more expensive things are. The slower the thing is, it's usually inexpensive, right? Because if it's slower and expensive, we don't really talk about it. right? So essentially, when you do the hardware, when you talk about the device controller and all those things, you assume that those slave things are, if you have disk controller, all it's doing in life is to do disk controlling, right? And it's cheap, rather than having the OS do it, the CPU do it, right? So you have this hierarchy where things which are fast are expensive, things which are slow are plentiful and inexpensive. So the key to get good performance is to always use the fast components, right? And not use the slow components. And the way you do that is you move things around, right? You move the stuff from the slow to the fast one. You move the stuff that you really need immediately to the fast component, so you get performance, right? So if I want to do something, I have to move it all the way up to the register. So if you go back to your architecture course, right? They talk about programs, the CPUs and registers and stuff. They're the fastest memory you can have in the machine. They're also the most expensive and most heat consuming and all those things. So if you wanted to read something from your optical disk, magnetic disk, or something lower down, right? Essentially, you move it. So if you wanted to read something on your disk and add one to it and store it back, right? Essentially, you read it from, say, magnetic disk to, it moves up the thing. It goes to main memory, it goes to cache, there are various levels of cache, and eventually comes to the register, right? And when you're done with it, you push it back, right? And that's what OS does most of the time. So a really good operating system will give all the things that you want up in the register, right? And the machine will go really fast. And really lousy operating system would have to go to the disk or the slower stuff all the time, right? And if you think about it, you don't really care about the past, right? You only care about the future. So what I want to do is, if I want to read, so right now I'm here. In the next step, I want to read some number from the disk, and I want to add one to it, and I want to write it, right? So if the OS waited for me to come to that point and say I want to read this stuff, and it has to move it across the stuff, then it's going to be slow, right? One way to speed this up is, before I come there, if you have it ready for me, I'm going to fly, right? So you want to have the cache where you know what the future is, and you bring it in, right? So if you knew the future, you can do great, right? It's very easy to optimize if you knew the future, because you know that I'm going to ask this, I'm going to do this stuff, move everything to be close to me, and I'll be perfectly fine, right? Many of us don't know the future, so you try to predict from the past what you're going to do, right? And that's where the smartness comes in. So if you think of operating systems going through different versions and stuff, there are people whose entire career is depending on trying to figure out, how do I predict the future based on the past? How do I predict the future based on what I'm observing? And that depends on different applications. If you think of different applications, there are different ways, right? And that's one of the ways that why you have different operating system versions, why you have different operating systems which are tuned for different people, right? To give you an example, right? If you have a matrix multiplication, right? And think of the really simple, naive way, where you kind of go like this, right? So if somebody knew that you're doing a matrix multiplication, right? And when you're multiplying, say, this and this, right? The OS can figure out, okay, I know that you're here, so the next thing you're going to do is go here, and the next thing you're going to do is go here, right? So if I can move these things before you get there, right? So while you're computing this, somehow these things come in here, right? Then you're going to fly. Then you're going to actually go as fast as if you have the whole register, whole matrix in a register, right? And as you can imagine, not every time you do this, simple stuff. I mean, there are, when you write programs, you have different ways of messing these things up, right? And that's one of the reasons why I think need to understand what your OS is doing, because if your particular operating system is aware of this and doing some optimization, and you're doing a matrix multiplication code, right? And mathematically, you don't have to go like this, right? You can go first this and this, then randomly pick another element of the row and do the stuff, right? But if you wrote a code like that, if you knew operating systems, you would say, no, I won't do that, because you are trying to defeat the OS notion of figuring out what the future is. If you're doing random, OS no longer knows what the future is. So you're going to run at the slow disk speed, right? Which can be pretty significant. I'll show in a couple of slides. As the processor is getting faster, that becomes even more critical, right? So, like I kind of alluded before, the main thing we do is called caching. You move the stuff around, right? And when you move it up the hierarchy, so for example, if you go back here, right, each of the faster ones have different characteristics. One of the characteristics is the magnetic disk is permanent. If you write something on it, it stays there. Whereas if you have something in the register, when you pull the card, it goes away, right? So you have to make sure that whatever you do, you move it up, you do the computation, then you have to write it back, right? If you don't do that, then essentially all the stuff you did just vanishes, right? If you want to, basically if you go to a PC, pull the plug, right in the middle, then you have you're in an undefined state, right? So the notion of cache is you have to move the stuff, you have to move the stuff before you need them, right? And the fourth bullet point, if it is in the cache when you come to that point, you have a cache hit, right? And you're trying to improve the cache hit because that piece of the program is going faster. If it's not there, you have a cache miss, meaning it's not in the cache, which means that somebody has to go look in the next level, see if the main memory, if it's in disk or whatever. And that's called a cache miss, right? And when you have a cache miss, you have to, you have to go keep looking till you find the actual object. Then you have to keep moving it back forward, right? So you move it from the hard disk to main memory to cache, and so on. So when you're trying to move the stuff, you have other stuff in your cache. Your cache is finite, right? Because it's expensive, right? So you have to throw something out. That's the cache replacement policy, right? So we'll see later on in the class so it's not only I predict what's in the future, I also have to predict the one that I'm throwing out would not be used for the longest time in the future, right? Again, if I knew the future, this is all excellent, right? So these are things that you would like to do because I want to throw away something. So I want to throw away something which won't be needed for the longest time into the future because I hope to keep things going. And again, since I don't know the future, I have issues. So, but that's the fundamental problem. You have the cache. If it's in the cache, it's called a cache hit. Excellent. If it's not in the cache, you have a cache miss. When you have a cache miss, you have to have a cache replacement policy. And depending on what the policy does, you'll either do good or at worst, you'll run at the hard disk speed, which is excruciatingly slow, right? Like if you notice, it took me like a couple of minutes, like 3 or 4 minutes to boot up this machine, right? That's nothing if I was running on the hard disk because it'll take me like 10 minutes to boot up because it's entirely on cache, right? And so the policies are, since the caches are smaller, how do I manage these things such that I get excellent performance, right? To give you a sense of, I don't know if you can read from the back, right? It's in the handout and it's in the textbook too. So essentially, you have the different kinds of memory, different kinds of, the registers, cache, main memory, and disk storage, right? In terms of the size, the registers are fairly small, less than 1 kilobyte. Whereas if you have a disk, it's, you can buy up to, I think Seagate is coming with a 1 terabyte disk. So you can buy a really humongous disk for practically nothing, right? And there are different technologies that you use to read them, to do the storage. And depending on the technology, the speeds can be different. So the registers are 0.25 to half a nanosecond. Whereas if you hit the disk, it's 5,000 nanoseconds or more, depending on where you are, right? So if the more you come to this side, your performance is going to be slow. The more you're going to be on the other side, your performance is going to be great, right? So some of these things, it depends on the hardware who manages these things, right? So if you buy a PC, and if you look at the specs, they'll say there's so much L1 cache, there's so much L2 cache, and what they are, you'll read in the architecture class, right? But each of the cache is faster than the other one, right? And some of the caches are maintained by the hardware. I mean, you don't have really too much control, in terms of the L1, L2. We'll see a little bit of that as we move forward. But a lot of other ones, the operating system have control. to move stuff from the hard disk and move stuff back to the hard disk is totally under control of the operating system. So if it knows in the future you're going to read something, it can move in and make things go faster, right? And so the last one is the backup storage. So if you were to pull so it's nice to keep things in the cache, but if you pull the plug halfway through, then you lose everything. So you have to keep juggling these things, right?
But
Yeah.
Which is faster, L1 or L2?
L1 is faster.
L1.
Yeah. Usually you can go by the size, right? Your L2 is usually in megabytes. L1 is usually in kilobytes, and some of the machines have L3 too, depending on the server kind of thing, right? Yeah.
I was wondering what the difference was between disk storage and main memory.
So main memory, this is again goes to the hardware component of it, right? Main memory is people talk about RAM, memory kind of thing, right?
Okay.
It's usually faster, more expensive. So if you buy a typical machine, you maybe have 1 gigabyte of memory.
Your main memory is the RAM and the disk storage, just your hard drive?
Hard drive, yes.
Okay.
Yeah. We'll go. I mean, we're dedicating one module for main memory management and disk management, but at the higher level, one is slower, one is faster, right? And does that answer your question? So there's another type of I/O that you can do from a program perspective to get good performance. How many of you have done asynchronous I/O in your programming classes or for other purposes? Okay, good. So I didn't see anybody raise a hand, right? So from an application perspective, there are two kinds of I/O, right? You can do a synchronous I/O or you can do asynchronous I/O, right? Synchronous I/O is what you typically use. So when you say a read, right? When you use a read or scanf or something from your C code, essentially you're doing a synchronous I/O, which means that if you say read I, right? When you come here, at this point, you have the value of I, right? Which means that read will not return till your value is read into the value I, and it won't come back to you, right? So that's the program that usually you teach in the undergrad programming class. It's fairly sequential, easy to understand, and very slow, right? Because it has to wait for the stuff. So if you have, like for example, you're writing a code like this, right? Can you read this? Right? There's read I, there's a read j, and then I say j equals I times I, some calculation, right? If I do this sequentially like this, the OS will not return till I is read, right? And OS will not return till j is read to this point. So when I come here, both of them have to be read, right? And that seems easy to understand, right? But in the case where I and j come from different things, right? So if both of them are coming from the same point, I have to probably wait, right? But say I is coming from this disk and j is coming from this disk. There's no reason for me to wait here for I, because I'm not using I anytime soon, right? So what I would like is somehow say, till I hit this point, I want to start this, I want to start this, right? And I'm going to wait here, and somehow I know that I have I and j. Only if I have I and j do I go to this statement, but I can do these things in parallel, right? And you can do that in your application program. In fact, most of your application programs commercial programs would do something like this, right? Because they know what they're doing, they know that they have to read this, they have to write this. So you issue a whole bunch of reads, a whole bunch of writes. And sometimes you don't really care. If you do care, you have to wait right there. But if you don't care, you can get these things going. So from application level, you can get good parallelism by using asynchronous I/O, right? And you may see it with your Windows event-driven programs, right? You can have exceptions or so a lot of programming languages give you syntactic sugar to make it easier, right? But fundamentally, it's more complicated unless you understand that these things are going on. So probably you don't teach that in the programming 101 kind of class, because you have hard enough time to keep track of what the program is doing. Now you have to say, when I come here, I may not be valid, right? I is undefined till I'm sure of this case, right? So that's the notion of That's what we are showing, trying to show what that means for kernel, right? So when over on the left you have the synchronous I/O, right, where essentially when you do a read, right, if you follow that line, right, your read has to go from your user process, your C program, to the kernel. It has to go all the way down. If it has to go to the device driver or what have you, right? And then when the results are back, are ready for you, you get the response back, right? So essentially at this point, when it comes back to you, everything is fine. You don't need to know anything. Whereas the asynchronous I/O model, I come down, right? It hits the appropriate kernel thing. And the kernel says, okay, I know that you have this pending, right? When I have the answer ready, I'll send an interrupt to you, right? I'll send a signal if you've used signals in C, essentially to say that is, that data is ready. So you get back, right? And eventually the kernel finishes this stuff and then returns the returns control, makes you interrupt, right? So if you want to use this kind of programming model, you have what is called software interrupts or soft interrupts, right? Essentially you're trying to tell the application, you are waiting for something, your data is here, right? This is different than hardware interrupts. So OS has a notion of different kinds of interrupts. So for a program, it's not that urgent to tell your application that you have something to read, because your application can probably wait, right? Whereas if it is something about, so say you're doing a CD burning, right? Many of you may have coasters when you do the CD burning and something stops or something, the thing goes up, right? Because there it has to burn at a certain rate, certain speed, and so on, right? So the OS can say, I have different kinds of interrupts. Some are more important, some are less important. And the software interrupts are usually less important. And we'll see there are more harder interrupts, right? That kind of leads into the notion of, we talked about interrupts and what we really mean by, what kind of interrupts. So there are the hardware interrupts, which come from devices. The software interrupts, which come from stuff like this, the kernel notifying the application that there are interrupts and stuff. And there are different priorities. Depending on what interrupt, you have different priorities, right? And some of the interrupts can be disabled, right? Because if you're doing something more important, you don't want to be bothered by less important stuff. So if you're doing something on the hardware level, you don't, so all the interrupts of those are wait, right? There are some interrupts which cannot be masked, right? These are mostly you learn from your architecture class what these are, right? These are, architecture gives you a lot of these interrupts. So essentially, if you're trying, let's say you're trying to shut off the machine, right? You press the power button, right? That sends an interrupt to the CPU to say, power failure imminent interrupt, right? That's usually considered non-maskable, which means that you tell the CPU, I'm going to shut down the machine, I'm pressing the power button, right? You have to take action. You have to flush your buffers or whatever, right? Because in a couple of seconds, you're going to go away, right? So even though it's not coming in a convenient time for you, you don't care, right? So those are non-interruptible things. But so depending on if it's that important, that serious, you have it non-maskable. If it's less serious, you can mask it, right? And traps are the way that applications generate something into the system. So interrupts created by a application is called a trap, just for ease of notion, right? And the way you use the place you use a trap is a system call. We'll see that in a few slides, right? So those are a couple of techniques that we'll get back to over and over again, in terms of what do we mean by resource management and what kind of resources we have, right? So now a few stuff. I mean, how do you interact with the operating system, right? So when you say operating system, so when you look at Windows XP, right, there's an operating system core underneath, and then there's a lot of other stuff, right? So this defines how do you interact with the operating system, and you can interact either with the command line interface, right, which is the older Unixes, right? Or you can interact with the GUI based, if Windows or Mac, when you boot up, it comes with the graphical user interface, and you can click and start those things. And you, in the old days or in mainframes, you have a notion of batch processing, right? So for example, the main Notre Dame, they probably have computers which are processing lots of data, right? So for example, if you're working on campus, your time and time sheet and all those things are being processed to get you paid, right? Those computers are operating on a batch because you know what they have to do. I mean, there's no user interaction. They're doing their job. I mean, you don't have to do anything interactive. So those fall under the batch processing. But things that you interact, it either is a GUI based or command line based, right? So the way that you access these system calls, access the kernel from an application perspective is through system calls, right? And system calls isn't, so let me erase this stuff. So let's assume this is the kernel and this is the user, right? So when you write a C program, you have to somehow at this point get into the kernel, do what you have to do, and then get out, right? And getting into the kernel means now you're going from unprotected to protected, right? So you can't just waltz in. You have to go through well-defined points, right? Because you're now elevating your privileges to go in there. And one of the ways to elevate this thing is through system calls, right? System call essentially creates a trap. It essentially creates a software interrupt to the operating system to say, this user wants some service, right? So they come up here, you make a system call, and system call tells you what function should happen, right? And system calls are defined by your API, right? Your word programming model, right? So there are different APIs. So you might have heard of Win32 API for Windows, POSIX API for Mac, Linux, or Java API for whatever, right? So usually when you read C, right, C follows POSIX API. So when you see a read, right, in C, right, that's a POSIX API that tells you how to read. I mean, that defines what it should do, right? So your operating system has to say what model it follows for a programmer to talk with you. So if you look at the specs, it'll say, this is a POSIX-based operating system. That means you have to follow a POSIX-based code.
This is probably a more complicated question than ask for a simple answer, but could you briefly explain what the kernel is? I really have no idea. Is it part of the operating system?
Oh, it is the operating system.
It is the operating system? Okay.
So yeah, okay, OS is the same as kernel, right?
Okay.
Usually you use that to differentiate between real hardcore OS and the GUI stuff on top of it, right? It's kind of hard to define that. So the Windows GUI system, right? Because that's what Microsoft does not sell you the underlying core, right? In the class, we're looking at the underlying core. So that's usually called the kernel. And then you have the other stuff, right? For example, if you install Microsoft Windows, right, you have some free software install along with it, right? That's definitely not part of an OS. I mean, that's something, right? But came with your OS, right? So, sorry, yeah. So kernel is the hardcore stuff, right? So, yeah. So the kernel is the one which does, whatever it wants, whatever services you want, and you have to come here and make a system call, right? And so the language that they speak is defined by these APIs. So it's system, Win32 or POSIX or whatever. So using that language, let's say, the system call to read something is read, right? So you have to do a read system call, which means that the system call has to create a trap, a software interrupt, to tell the OS that you want something to be read, right? So in the next slides, we'll see what that entails. To give you an example, this is a pseudo code, in POSIX, for C, right? So essentially, so it's not that there may be, it's not meant to be to highlight C programs, but as a way to make point, right? So for example, in this particular case, right, you first write something, right? So when you write, depending on the POSIX API, how many of you know C read-write calls? So you guys use C, right? So what did you use? Scanf? Okay. In terms of the programming language, right? There's scanf, right? Which is part of the standard input output I/O library, right? Which scanf does buffered read and write, right? I can think another word is cached read and write, right? We talked about that, right? So this underneath calls read, right? And read is not buffered. Read, if you say read 1 byte, it gives you 1 byte. So you guys are aware that printf and scanf is buffered, right? So can you think of one way where that affects you, that buffered notion? Think of what this one does. What do you expect this will do?
Put it out below on the screen.
Another option?
We'll put it to the buffer and then it goes to the screen for it.
Yeah. So if you put print hello, right? All this says is it goes into the buffer, right? And it's up because we are managing the buffer for whatever. Depending on the policy, depending on whatever is happening, it may go to the screen right now. Or it may go whenever it's convenient, right? So if you say print hello, that just means that it's went to the buffer, right? You must have faced it because if your program crashed right here, right? That's the first thing I noticed. When you're first starting to write C programs, that's the #1 complaint, right? Because students say, I have this code, it's crashing here, but I don't see hello printed, right? So there must be something wrong with the C compiler, or something wrong with the machine kind of thing, right? That's because, how many of you actually face that? Right? And essentially that's because it's being buffered, right? It's being buffered and it doesn't get flushed for whatever reason. So for example, on a standard C compiler, the heuristic that they use is if you have a \n here, and if it's going to standard output, then it's flushed immediately, right? But that's just a heuristic for specific things, right? So anyway, so that's the buffered I/O, right? That you used in the class. So that essentially goes to a read call, which has no buffering. So when you do a read 1, right? 1 is your standard standard out. Standard out, right? So the first sentence is similar to your fprintf std out input file. That's it, right? And the second read, the first 0 means standard in, right? Right.
Is that so? That first argument is to write and read is whether or not it's in or out.
No, that's the file descriptor. So if I have another file open, that number could be different, right?
The file to open, or the part of the buffer that you're accessing,
So when you look at when you did this scanf and fprintf, right? You don't implicitly state where it's going, right? When you say printf, right?
Yeah, you don't say where it's going.
Hang on. So this is equal to right?
Yes.
This is a shorthand for this, right? But let's ignore this because it's a shorthand, right? Essentially, you only do this, right? fprintf standard out this, right? Standard out is 1. That's a heuristic you don't have to know, but that's you know, right? But if you look at the next segment, right? This component, it tells you the FD that you get, right? It's more explicit, right? But we don't have to worry about precisely what the system call is. Like, that's a different course in some sense, right? How to program and stuff, right? So for example, the last sentence is your fclose, file descriptor, right? That's just similar to that one, right? Whereas when you have the buffer, it's doing some buffering, and whereas here it's the raw thing, right? So you have the scanf from your standard I/O library, and C, the POSIX is the read and write, right? And this goes into a sysread, right? Which you're not supposed to look at because that's the way you actually call the operating system, right? And I'll tell you in a little bit why you do that, right? But for now, so this is a simple call that you would do, right? So if you think of them as fscanf or whatever, so if you look at the next line when you do open, you pass some flags, right? You say, I want to open the file. This is similar to your, you say r plus, write plus in fopen, right? You want to say, I want to open it for reading or writing or whatever. And those all translate to these cryptical bit fields, right? Essentially, you pass, so that's how you interact with our OS. You say, I want to open a new file, whatever, name, and I want to open in read mode, write mode, create mode, what have you, and then you call the kernel, right? Yeah, so here's another way to look at it. So if you call the printf greetings up there, when it goes to the standard C library, it essentially becomes a read call and read or write call, and that goes into a system to the OS or to the operating system kernel to get your services, right? So at this point, it could be a read call, right? It could be an open call, right? So instead of rather than having a different trap number for different system calls, right? So one way to do that is to say, OS, I'm going to do a read call, I'm going to do a write call, or whatever, right? What you typically do is, what machines do is, there is one system which says, I'm a system call, and you have some table, right, which says that if I make a call number, 10, it's read, right? 11 is write, or whatever, right? You define some number somewhere, right? And the convention you use is, I make a system call, I do a trap, and in some known location, like some memory, some register, I leave this number, right? So the kernel knows inside that when you come here, when I get a trap, it looks at that location to see what you're trying to call, and then it makes an appropriate call, right? I'll show you code examples from how machines actually do that later on. But operating system uses lots of these things. They have a table to disambiguate where you want to go, right? And you have to have some number which says where I want to go, right? So if you mess up this number, then you have a disaster, right? And if you have Unixes, if you go to that user include syscall.h, it gives you a list of all the system calls that you imagine and what the corresponding number is, right? If that table gets messed up, then here you are saying I want to do read, and so you don't really say I want to do read. You say I want to do system call 43. The system calls, if the kernel thinks that 43 is for write, then it's undefined, right? Because for each of the call, the parameters are different. So if you go back here, if you look at the stuff, the open has different base number of parameters than write and read. So this function has to assume what the input parameters are. So you can't just randomly change these things, right? If you do, then you'll get a code dump, right? You'll have a really bad code dump. So that's where all the API comes in. So when you build this kernel, you have to have this table that when you're building, your applications know what the number is and you know what the kernel number is. System call is a privilege trap. So essentially, you're not losing anything because all you tell the kernel is, I want to make system call, here's a number, right? So there is some checking done to make sure that you're doing what you're supposed to do, because at this point, when you say the kernel, you are privileged, you're a supervisor, right? Privilege mode, right? And even at this point, there are a lot of intricacies that you have to follow, right? So if you look at the programming language perspective, you have to know that something has to be in this register, something has to be here, something has to. The error code that it returns are a lot more complicated than what POSIX wants, right? And that's one of the reasons why you have this next level indirection, right? For example, this kernel may return something to say you're out of paper, right? But the POSIX, there's nothing called out of paper, so all it says gives you error saying error, right? So if you look at the your C functions, some of the error functions will say error, right? Error, and you're supposed to figure out, right? That's because the kernel actually knows and it tells you what it is, but you can't return it from the POSIX side, right? So usually you have these two levels of indirection where you write something in POSIX, then it goes into what is very specific for that particular machine, and then it makes the call, right? So that way, this is how you get into the right function within the operating system. Is that clear? We're not done yet. We need to next figure out how to pass arguments. But for now, this is how I say I want service for function read, right? So yeah, actually, there's a better graph here. So you have the kernel mode and the user mode, right? So I make an open system call, right? Which means I need to figure out what's the function number for open, put that wherever I need to put, right? And then I do a trap. OS gets a software interrupt. Software interrupts are typically not that important. So if there's anything hardware it has to do, it takes care of those. And then it eventually comes to the software interrupt, looks at the number, right? And it knows that the number, let's say you put was I. It goes into some table, figures out I maps into, you have to put a function there, right? Some C function. So it goes there and does what it has to do for you, right? So that function implements the functionality for open inside the kernel. And this way, you get the particular code. And whenever it's done, it returns back to you, right? Does that make sense? So the next question is, so that tells you what the function you're trying to call, right? The other one is, what are the arguments, right? The parameters to your call, right? So there are different ways to pass the parameters. So in the case of, if you say read, let's say 1, 2, 3, right? I'm just making these stuff up. But how do you pass this 1, 2, and 3 to the kernel? That's what we are trying to figure out, right? So the simplest way is to pass them in registers, right? So has any of you used DOS? The real DOS, not the DOS under Windows NT or something, but the real hardcore DOS, right? So if you use that, the old DOS, right? If you wrote code for that machine, you have to put certain things somewhere. You have to say, the B register is for passing the parameters, C for passing parameters, and D for getting the results back or something. So there's a certain convention. So before you make the trap, I have to put the right parameters in the right registers. And then when I'm done, I expect the values in the right register. Right? It's simple, but it's kind of annoying, right? Because you only have few registers, and you're using registers for this purpose. You can't use it for anything else, and it's kind of annoying, right? So the other way to pass is to put them in some memory, right? So the other way to do that is put them in some memory, right? All the parameters that you want. So in this case, you put 1 and 2 and 3 in the thing, and then you pass this address using a standard mechanism, right? So that's what Linux and all would do. Essentially, you pass the argument into a block. You allocate a block, right? You allocate a block. You copy all the values from here into that block, right? You can't just pass your user stuff. We'll see why later on, right? Because you don't want the kernel to be writing into your space, because kernel is privileged. You're not, right? So you don't want the privileged stuff to be writing stuff directly. So you copy everything into this privileged space, and then it copies it back, right? You probably don't care, but the kernel cares. He doesn't want to write into his stuff. So the other mechanism is to pass it on the stack, right? And that's more flexible, because you basically pass all the values that you want to send into the stack, and then you take it back, right? The specific mechanism of how stacks and all work is probably covered a lot more detail in compiler class, right? Essentially, how many of you know about stacks and stuff? So where do you, from algorithm class or? Data structures, okay, algorithm, okay. So compilers use a lot of that. I mean, they push all the value, when you call a function, they basically pass all the values into the stack and so on. So the key here is it's on the protection, right? You can't pass it into the user stack. You have to pass it into the kernel stack, right? Some of the stuff I'm saying about the protection may not be obvious to you, because we covered it at the last, right? So essentially, what I don't want to do is, if I have a program, suppose in my program I have a variable called I, a variable called j, right? If you pass this value and this value to kernel, right? if the kernel has to mess up, because kernel is privileged, you can go anywhere, you can write anywhere, right? So you can write here, you can write here. You won't get any trap because kernel is, you can do anything, right? But you don't want that because then it can, if you do something wrong in your program, you get no feedback because the kernel can't write anything, right? So you always want to copy it into something. So when you do this pushing into the stack, you have to make a copy into the stack because otherwise bad things can happen because remember, when you're in the kernel space, you can do anything. There's nothing you can't do, right? I can write through your program. I can destroy anything. And if you want any kind of stuff, you have to write to the user program, right? We'll see what the protections are later on in the class, right? So essentially, this is what happens. So you have, so if I want to make a system call, right? I figure out that the function I want to do is 13, right? I make a call, and it gets routed through the routing table, right? And whatever address I want the parameters, I put them somewhere, and I leave the address x of the parameters into some known place, right? So the functions can expect the parameters that I passed by looking at the register, right? So I create a table for all the parameters and pass the address x into some register, and that way you get the values, right? So this way, when you want to make a system call, you make a trap. You have to figure out what the function number you want to call, right? You put the parameters in some location. You pass the register to the kernel. So this way, you can pass a variable number of arguments, right? The specific function has to know what arguments are and how they are being sent, and the specific number depends on, you know, the some table, right? So if any of these are, you have some, variation, you have catastrophic failure, right? So this is what happens if you take operating system from different versions and try to run it on the same machine, right? So if you go from Windows XP to Vista, right? Microsoft is free to say, we're going to define a new set of system calls, a new set of system call numbers, or what have you, right? If you take the exact same program and run it, then you are calling open. Windows Vista says that's close, and all bad things happen, right? So we'll stop at that point and we'll continue with it on Monday.